Here we're going to look at Hardy-Weinberg. So Hardy-Weinberg allows us to go and look at allele frequency and genotype frequency within populations. So what do we mean by genotype frequency and allele frequency? Well, these are two different equations that we can actually go and use to go and predict the different frequency, or whether it's a different genotype or a different allele. So they have two different equations. So in terms of our genotype frequency, we have p squared plus 2pq plus q squared equals 1. Our allele frequency is p plus q equals 1. So we can see here, in terms of the genotype frequency, we're actually looking at genotypes themselves. So whether it's homozygous dominant, heterozygous, or homozygous recessive. Whereas the allele frequency, we're only looking at dominant or recessive alleles. So genotype frequency, we're looking at 2. Allele frequency, we're only looking at 1. So we use our genotype frequency for questions like, if 81% of a population is homozygous recessive for blue eyes, calculate the frequency of the homozygous dominant trait. Whereas with allele frequency, we use it for equations such as the allele recessive Y occurs with a frequency of 0.8 in a population. Give the frequency of our dominant Y. So, just to give a better view of what these actually mean, we can go and try and picture it. So, in terms of genotype frequency, we also need to go and know which each part constitutes as. So when we're thinking of our p squared, that's our homozygous dominant, our 2pq is our heterozygous, and our p squared is our homozygous recessive. So remember, you're always looking at two alleles here. So p squared, you're looking at both of the dominant alleles. So you'll have two dominant alleles, one for your mother, one for your father. When you're looking at the heterozygous, you've got a dominant and you've got a recessive. And when you've got your recessive, you have two recessive alleles. When we're looking at our allele frequency, remember we're just looking at dominant or recessive, so P plus Q. So P is equal to our dominant allele, Q means our recessive, so we're only looking at one allele here, so we can see one chromosome. So we have an example question. A population of summer squash plants produce only green and yellow fruit. The percentage of plants producing yellow fruit in this population was 36%. Use the equations to calculate the percentage of plants that are heterozygous. So we know that they're looking for the yellow fruit here. The yellow fruit has a percentage of 36%. So yellow is equal to 36%. Now, when we're working with these equations, we always have to have in decimals. So we know that 36% is also 0.36. So our yellow is going to be our homozygous recessive. So we need to go and think about our equations. So p squared plus 2pq plus q squared equals 1. So that means that we're looking at our q squared here. So q squared is equal to 0.36. That must mean that q is equal to the square root of 0.36. So q must be 0.6. So we found out q. So we can now use our allele frequency equation, p plus q equals 1, to go and find out our p. So p is equal to 1 minus 0.6. So that must mean that p is equal to 0.4. So we now have our p and we also have our q. They want us to go and find out the heterozygous. So heterozygous is going to be our 2pq. So 2pq is equal to 2 multiplied by q, which is 0.4, multiplied by 0.6. So 2pq is equal to 0.48. Now, we also have another equation here, so another question. So in a population, the frequency of the allele for tongue rolling T is 0.4. We need to use our equations to calculate the percentage of people which are heterozygous. Okay, so they've given us T. We can see it's dominant here, and it's 0.4. So T is equal to 0.4. It's dominant. So we know it's alleles because they've said that it's the actual allele here. And we can see that T is only one version. Okay, so it's not a genotype, it's an allele here. If it's a genotype, we'll see 2 letters. So we need to go and calculate what this is in terms of our equation. Okay, so if it's an allele, we're using P plus Q is equal to 1. So we know it's the dominant, so that must mean that P is equal to 0.4, which must mean that Q is equal to 1 minus 0.4. So Q is equal to 0.6. So we have our P and we have our Q. They want us to go and calculate the heterozygotes. So we use our longer equation. So P squared plus 2PQ plus Q squared equals 1. Heterozygotes are 2PQ. So 2PQ is equal to 2. Our P is 0.4. Our Q is 0.6. So 2PQ is equal to 0.48. If we wanted to go and think a bit more, a question with a bit more complexity, we have one here. So in a population of wild rats, 51% were resistant to warfarin. We need to use our equations to estimate the population of rats that were heterozygous for warfarin resistance. So we need to think really carefully about what we're actually working with here. So we know that 51% are resistant to warfarin. Okay, but we also know that the heterozygous are also resistant to warfarin. So that must mean that it's a dominant allele. So remember, if we have a dominant allele, you only need one version of it for it to be displayed in the phenotype. So that must mean when we're thinking of our equation, our P squared plus 2PQ is equal to 51%. Okay, so remember you only need to go and have one version of that allele to actually have it displayed in the phenotype. So P squared, it's homozygous dominant. They are resistant to warfarin, but so are the heterozygotes because they've got P here as well, one of the dominant alleles, so they are also resistant. So we need to go and think about how we can actually go and figure out what P and Q actually are. So we can't actually rearrange this formula here to go and find out what either of them are. But because, remember our equation, we're missing our Q squared here. We know that Q squared will be the remainder of this equation. So Q squared must be 49%. So Q squared is 0.49, which is also equal to Q equals the square root of 0.49. So Q must equal to 0.7. So we now have Q. So again, we go to our allele frequency equation. So P plus Q is equal to 1. So we have Q, we now need to work out P. So P is equal to 1 minus 0.7. So P is equal to 0.3. So we have our P, we have our Q. They want to know the heterozygotes. So again, we're thinking of our 2PQ. So 2PQ is equal to 2 multiplied by P, which is 0.3, multiplied by 0.7. So 2PQ is going to be equal to 0.42. Our last one here, okay, we have some humans have a genetic resistance to infection. A recessive allele gives increased resistance to infection by malarial parasite. In a population, the proportion of babies born with homozygous for this allele is 0.01. Use the Hardy-Weinberg equation to calculate the expected proportion of heterozygotes in this population. So we know it's a recessive trait. We also know that we're looking at the homozygous here. So we're looking at the homozygous recessive. So we look at our equation. So p squared plus 2pq plus q squared equals 1. So we're looking at our homozygous recessive. So we're looking at our q squared. So q squared is equal to our 0.01. So then that must mean that our q is equal to the square root of 0.01. So q is equal to 0.1. So we now have our q. We now need to go and think about p. So again, we go to our allele frequency. So p plus q equals 1. We have q. So p is equal to 1 minus 0.1. So p is equal to 0.9. So here again, they want to know about the heterozygotes. So we go back to our genotype frequency. We want to go and think about 2pq. So 2pq is equal to 2 multiplied by p, which is 0.9, multiplied by q, which is 0.1. So 2pq, also known as our heterozygotes, is equal to 0.18. So we do need to remember that our equations are only true if we bear in mind a number of different constants, okay? So we need to go and think about the conditions that need to apply. So we can't have any mutations occurring within the population. Mutations bring about new alleles, okay? And new alleles is something that we don't want. We don't want new alleles introduced. We don't want any new alleles being coming into the population or going out of the population either. Okay, so they can't leave or they can't come in because that will change the frequency of the alleles as well. We can't have any selection either. Okay, so we can't have any specific trait being favored, okay, or eliminated either. Mating needs to be random, okay, so we need to have random mating occurring, okay, so we can't have any mate specifically choosing one phenotype over another. And we also need to make sure that the population is large, okay, so we don't want to go and have any genetic bottlenecks. We don't want to have any small populations either. Okay, guys, so that is your Hardy-Weinberg equations.